Oh. Hello and welcome back to Calculus 1. We are starting the third part of calculus, which is integration. The lecture is titled Antiderivatives because derivatives and integrals are opposites of each other in a sense they undo each other. And that's the way we actually learn and understand this. If I say that the derivative of x squared is 2x, then I will say that the integral of 2x dx, which is the notation for integration, is equal to x squared. Now, this is not the entire story, so I'll have to add something eventually. Now, what is the derivative of x squared plus 3? Still 2x, right? And is there a way for me to now get my plus 3 back?
Plus c?
Yeah. There is no way to get this plus 3 back, which is why we have to add this plus c every time we integrate. I'll give another example of d dx x squared minus, let's say, 10. It's also 2x, and the integral of 2x dx is going to be x squared. So we really need this plus c, because this plus c is telling us that there could have been some constant that derivative destroyed, and we don't know what it is. So such is life, right? Now, there are ways to compute it if you have something that is called an initial condition. Now, I need to explain what that is. Now, I want to ask you here, if you are looking at these functions, all of them, they can be graphed as I have this one, which is x squared. I have the one that is going through 3, and I have the one that's going through negative 10. They're all the same shape. All this constant is doing is moving it up or down, right? So this plus c business is actually going to have infinitely many of these, and they're going to fill all of the space. But no two will go through same points. So, if I have a point xy given, that point is known as initial condition. And we can use it to calculate c, value of c. So let's say that the point given to you, so say the point given to you is 2, 7. Okay. So if the point given to you is 2, 7, you have that, we use capital F of x. I'll explain that again later. We have capital F of x is equal to x squared plus c. So just plug in. You have 7 is equal to 2 squared plus c. 7 is equal 4 plus c. C is equal to 3. And you determined that the antiderivative is x squared plus 3. So you were able to calculate this function and single it out of all other functions. But that's just because 2, 7 was given to you. If you don't have 2, 7 given, and most of the time you don't, you just leave it as the antiderivative, which is x squared plus c. So what we have done so far is we said that the integral of some function f of x dx is equal to the antiderivative plus c. So this capital F over here is called antiderivative. That f of x is called antiderivative. And what you have for it is to check. So this is like a concept formula. And then to check, all you need to do is to take the derivative of antiderivative, and you will get the original f of x. This is the reason why I liked integration a lot, even though it's harder than derivatives. I liked integration because at the end of each problem, it takes me 1 second to check, because I can take derivatives quickly. And if it matches, woohoo! So your differential equations will heavily depend on all of this. Now, the vast majority of formulas for antiderivative you already know because you know your derivatives. You're just reading all of those formula backwards. The only one that is different is the polynomial one. Because for derivatives, you have n x to the n minus 1. Now you're going to have some form of n plus 1 because the powers are supposed to go up in the integration, where the powers go down with differentiation. Remember, they're opposites of each other. So let's take a look at the formulas which you guys already know. You know that the derivative of a constant c is 0, which creates the integral of a constant dx, which creates the integral of 0 dx to be 0 plus c, and you get your c back. The derivative of just x is equal to 1. So integral of 1 dx is x plus c. You know all of these formulas from before. We are just writing them differently now. Here is the one that is different. So in the past, the derivative of the polynomial was nx to the n minus 1. Now integral of x to the n dx is going to be x to the n plus 1 divided by n plus 1, and then you have your plus c. What's the derivative of e to the x? Very good. So what's the integral of e to the x? Exactly, the same. What is the derivative of ln x? 1 over x the integral of 1 over x dx is ln absolute value x plus c. You have to put this absolute value. I will explain that in a second. I just need to write all of this out. I'm going to now write 6 trigonometric ones and a single inverse. So the derivative of sine x is cosine x integral of cosine x dx is sine x plus c. The derivative of cosine x is negative sine x. The integral of sine x dx is negative cosine x plus c. The derivative of tangent x is secant squared x. The integral of secant squared x dx is tangent x plus c. Note that integral of secant is not a basic function. You get to learn that one in Calc 2 actually. So the derivative of integral of sine and cosine are basic integrals. But the integrals of secant, tangent, cosecant, and cotangent are not basic integrals, which is interesting. So the derivative of cotangent x is negative cosecant squared x, which means that the integral of cosecant squared x dx is negative cotangent x plus c. We have the derivative of secant x, which is secant x tangent x, which means that the integral of secant x tangent x dx is secant x plus c. And finally, well, one more after this actually. So we have cosecant x, which would be negative cosecant x cotangent x, and the integral of cosecant x cotangent x dx is going to be negative cosecant x plus c. Now I get to say, finally, even though there are other 5 inverse trig functions, this one is the one that it's most important. Derivative of inverse tangent of x is 1 over 1 plus x squared, which means that the integral of 1 over 1 plus x squared dx is going to be the inverse tangent. You can also write it as arctan if you want. And plus c. All of these formulas, and then also the other 5 for inverse trig, are given to you in your section 4.9 in the textbook. And all of these formulas, as you can see, are just backwards derivative formulas. Note that, this one more time, note that tangent, cotangent, secant, and cosecant are not basic functions in terms of integration. They are for derivatives, they are not for integration. And all of those will be presented to you in Calc 2. Right now, we are only dealing with what the basic integration functions are. So we now need to just take a look at few of these things. So I need to box all of the, actually, you know what, I'm just going to box the integration side. I'm just going to box integration side. And if you understand that the integration, right, is backwards derivatives. Right. So I need to put few remarks before we go on and do problems. Remarks. Always wanted to put that word. There you go. I used it. So, integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c. This was the one, and I mentioned, and I said polynomials. That was so not true. There's more, right? We all agree that integral of x to the 9 dx is a polynomial. You get x to the 10 over 10 plus c without thinking, right? Because if your exponent n is 9, then plus 1 is 10, and you're just done. So polynomials, yay, a joke, right? But what else follows in a category of x to the n? Well, we have all of the roots as well, because the exponent of a half is a square root. Exponent of 1/5 is a fifth root. So if I have a problem that says a fifth root of x dx, that also falls in the same category, because I can write it as x to the 1 over 5, and it becomes my simple n plus 1 problem. So x to the 6/5 divided by 6/5 plus c, which is 5 over 6, x to the 6/5 plus c. So if you have any kind of a root, just on x obviously, you are still using the same rule. So this rule over here is going to go for all types of problems. There's one more. Integral of 1 over x to the 6 dx. Well, that's equal to the integral of x to the minus 6 dx, which is x to the minus 5 over minus 5 plus c, which you can nicely write as negative 1 over 5x to the 5 plus c. So all three cases can be converted, so they are either R or can be converted into the formula up there. Which is the one that it's excluded? Well, it's the only one that would give you 0 in denominator, right? When your n is -1, then -1 plus 1 would be 0, and that would be bad. X to the 0 divided by 0. So excluded, and I'll use the red arrow now. Excluded is integral of 1 over x dx, because n equals -1, and that will create a problem. However, we are lucky that, I mean, this is the way that the nature works. It's not we are lucky, it's just that's what it is. There is an ln formula for this, and I did say I will explain the absolute values. So first off, when you think about all possible exponents that your n can take, the only bad one is a -1. That's the only bad one. Everything else is okay. So if you have them as fractions, as you have them as decimals, as you have them as whole numbers, or negative, positive, doesn't matter. All of them work except one, -1. But we already had on this list what's happening, right, with -1 exponent. So now we'll just write that one down. And the only thing that I didn't do yet, and I promised I will, is why you must have absolute values there. Why are you losing points if you don't put them? So when you look on the left-hand side, this particular 1 over x function has its domain as -∞ to 0, union 0 to infinity. Meaning, you can plug in any number, positive or negative. You're not allowed to plug in 0. Now, ln x without absolute values has a lot of similar features. Ln x without absolute value would just have this piece as a domain, and you still can't use 0 because ln has the asymptote at 0. So that all matches. The only thing that I need to make happen here is to allow for negative numbers to be plugged in as well. Because imagine if I am allowed to plug in a negative 2 over here, and I am. 1 over negative 2 is just negative 1/2. Without absolute values, I would not be able to plug in negative 2 for ln, because it's not in the domain. But if I put absolute value, and I put negative 2, then negative 2 absolute value makes it a positive 2, ln of positive 2 I can compute. So this absolute value on the argument of ln just make sure that the domain on both sides of the equation are the same. So that absolute value is not there for decoration. So make sure you have it 100% of the time when you're solving these problems. I'll just go here. Recall. That was a medium effort over there. So recall that ln x is just one-sided. And that will help you with understanding that absolute value will bring the other side as well. Great. We have to list 3 properties, and then we can do a whole bunch of problems, and we're done with 4.9. Properties. Number 1, integral of c f of x dx. You can kick constant outside of the integral. Guys, this is the property that you had for limits. It's the property you had for derivatives. And now you have the same property for limits. If there is a constant, kick it outside. Deal with it later. At the end. You just multiply everything by a constant. Same rule you had before is still here. The following 2 rules are also the same rules of linearity. So if you are adding 2 functions, f and g, so f of x plus g of x, in the integral, you are allowed to split this into 2 separate integrals. So each function gets its own integral. F of x dx plus integral of g of x dx. So we have this rule, and you had the same rule limits and same rule for the derivatives. This rule just allows us to work on a term wise, right? So if you have x squared plus 2x, you can just focus on x squared, integrate it separately from the other 2x, I think I said. Number 3 is the same rule for subtraction. So f of x minus g of x dx is going to give us the integral of f of x dx minus the integral of g of x dx. And that completes our properties. I was about to ask. So what happened with the derivatives? What if they're multiplying? Product rule happened. A special formula happened and you were able to deal with the product. A special formula happened, and you were able to deal with the quotient. Do we have special formulas for integration? Yes. Are they in Calc 1? No. So multiplication you will be dealing with in Calc 2. It will be called integration by parts, and then some of the quotients will be in your partial fraction decomposition and so on. So the multiplication and division formulas will show up, and you will deal with those when you're in Calc 2. The only formulas we deal in Calc 1, we only have 5 sections of integration, guys. That's all we have in Calc 1. And then you are going to have 4 chapters, well, 2 actual full chapters of integration in Calc 2. About 60-65% of your Calculus 2 is straight up integration. Right? So this is it in terms of what we need to know. When you integrate, you have to put plus c, because we don't know what constant was there originally. You can find that constant by using initial condition if it's provided. If it's not provided, you can't. We know that all antiderivative formulas are simply backwards derivative formulas, with the exception of the one that was polynomial rational radical, right? With the x to the n. That one had a different formula of xn plus 1 over n plus 1. You are going up in exponents. That one was taking care of 3 cases: polynomials, rational, and radical, meaning that those exponents can be worked out as some kind of power, which was x to the n, and then you can use n plus 1 over n plus 1. And the 3 properties, these are the properties of linearity, meaning that, and you had them the same for limits and the same for derivatives. With the warning that if you see multiplication, if you see product in Calc 1, you have to FOIL. And we'll see the examples now. But what you cannot see in Calc 1 are the problems that you cannot solve, which is like x times sine x. You can't solve that in Calc 1. It's a product, but you can't FOIL. The only technique that you guys have in Calc 1 is foiling. So x times x squared plus 3, that's okay for Calc 1, because you can FOIL x into x, distribute x into x plus 3, x cubed plus 3, whatever I said, and then you just use the basic x to the n rule, yes. So let's do a whole bunch of these exercise problems, and then we are going to start chapter 5, which is a lot more integration in life. So, integral of 3x to the 6 dx. We said we will use the rule to kick 3 outside and only focus on x to the 6. So 3x to the 7 over 7 plus c, which is, you can write it as 3/7 x to the 7 plus c, whatever. It's all good. Integral of 5 divided by 4th root of x cubed dx. How's your algebra? Let's see. So what should I have as an exponent? We kick 5 outside. Okay. Integral and x to the
negative 3 over 4.
Negative 3 over 4 dx. Very good. And now you will just add 1. So if you know your algebra, the rest of the stuff is gonna go very easy.
It's like 20x.
So we'll start with 5. We have x to the negative 3/4 plus,
4.
yes, 4 over 4. So I'll just put plus 1. Divided by negative 3/4 plus 1. And then plus c. Do not forget plus c. Otherwise you trigger my allergies. I become extremely allergic to you, and then that's a problem. Right? So don't trigger my allergies. We have 5x to the 1/4 divided by 1/4 plus c, which is 24th root of x plus c. Or you can put x to the 1/4. It doesn't matter. It's still good.
You're going to remember the plus c.
Oh, it's either plus c or it's minus 1. So it's, yeah, minus 1 per line per problem. Watch someone scores like a negative 7 on a test because didn't put any plus c on any of these. So look, if this problem over here is, let's say, 5 points, 1, 2, 3 plus c's, that's minus 3 already.
Really?
Yeah.
You mean just minus 1?
Would 1,
No,
2,
like, I get that.
3.
It's only like one part of the problem. You just minus 1. Everything else.
So that's how you would have it if you were teaching?
Yeah, I figured.
Okay.
Oh, that worked for me.
I'll help you get here. Don't forget any of these. You can have my chair. All right? But for now, don't forget any, right? And then you can change the rules and say, if you forget 3 plus c's, I'll just take minus 1. I was thinking of doubling, so it's like minus 2 per plus c.
Then you'd be losing points.
Exactly, that's why I said negative, exactly. Negative, exactly. All right, so what else? The integral of e to the x plus square root of x dx. Note that I put parentheses around. And we are going to learn very soon, in about, well, it's next lecture, that there is actually multiplication in between these. So you need that, you need those parentheses. Let's see what you got. So this is strange that I changed the password. My tablet is not asking me to update the password, so I'm using the old one, but my phone did. I just had, I don't know what's going on here. I don't understand how to do this.
Elon Musk. Don't confuse schooling with education.
Yeah.
I didn't go to Harvard, but the people working for me did. That's what I said. If you want to be rich, you don't go to school. You own stuff. If you want to be rich. When you go to school, you are guaranteed middle class. So you're not going to be poverty and poor. That's what you are paying.
No, with current education, there's no way that you can actually work out fine in terms of being rich and stuff, because everything is about conforming to rules. And when you conform to rules, you can't think outside the box to create something new. So you can't. One of the most retarded ideas I've heard is, oh, I'm going to school to be an entrepreneur. But what? That's contradiction in terms. Like, they're polar opposite of each other. Complete opposite of each other. You're going to school to learn how to be different? Oh, not only you go to school to be the same as everyone around you, because this is the same problem for everyone. Same rules for everyone, right? And then from one class to another class to another class to another class comes when 50 students and take you out one, and they all have the same problem with the same rules with the same. Right? That's the same. That's education. So we can rewrite this as, you don't have to, but we can rewrite this as integral of e to the x dx in this own integral, and the integral of x to the 1/2 in its own integral. You will be integrating it separately, so whether you write two separate integrals or you don't, it doesn't really matter. Your answer will have no integrals, so e to the x is e to the x, and integral of x to the 1/2 is x to the 3/2 divided by 3/2 plus c, or minus 1, and then plus 2/3 x to the 3/2 plus c. There we go. So I'm just going to bring up some of the examples that look spicier in the homework. Again, please keep in mind the level of integration that you are at right now is only going to be algebraic manipulation and then basic integrals, right? So no products, no quotients, and if you see any of those, you either have to FOIL or you have to do a long division. You just have to get rid of them in some way. There has to be a way to get rid of them. If it's trig, you will be using identities to get rid of the extra stuff. So the example that they give, this is problem 31, they want you to integrate 3x plus 1 times 4 minus x dx. As I said, the only thing you guys can do is FOIL in this example. Today is Saturday, right? Yeah. So FOIL. Now, don't forget to put the parentheses. You need to put multiple terms in there. So that's 12x minus 3x squared plus 4 minus x dx. Combine like terms. You can put the negative 3x squared first, then plus 11x, and then plus 4 dx. So now, what we do is integration. Now, without breaking this into 3 separate integrals, we're going to go negative 3 and then x cubed over 3, because the integral of x squared is x cubed over 3. Then we are going to take the plus 11, and then we have x squared over 2, and then plus 4x, and then plus c. 3's will cancel. Sí, señor. There you go. So that's that. Problem 37 is also nice. They say, how about x squared minus 36 divided by x minus 6 dx? So what now? So what do we do in this problem?
Division. You can get like x plus 6.
So we factor and cancel. Factor and cancel, and then we're good to go. So what are the factors of this? X minus 6, x plus 6. Very good, very good. So, x minus 6, x plus 6 divided by x minus 6. Don't forget the dx, not there for decoration. We'll see soon. So we have integral of x plus 6 to deal with, and that's simply x squared over 2 plus 6x plus c. So that's our calculation. Excellent. That's exactly what it is. Okay, so now we are going to go into chapter 5 and learn some of these rules. Learn what is this used for, right? The application of, the main application of integration and all of that stuff will be later in chapter 6, and then more integration techniques in chapter 7. So you guys are going to have a lot of that stuff. So we'll restart the stream. I'm gonna take a few seconds break, and then when we come back, chapter 5.